So, hi group. Today is my last day as an official member of this group, and that's why I wanted to share with you once again my excitement for machine learning. I want to talk with you about how this field started, where we're standing right now, and what amazing achievements to expect from it in the near future. I think that all of these aspects are especially interesting from a viewpoint of someone who was recently looking for a job, like I. So I did my master and my PhD thesis here under Burkhart's supervision. My topic was application of machine learning to the protein subcellular localization. My approaches, they were very much inspired by already existing approaches. However, having more data and having more sophisticated algorithms helped me to achieve successes. The successes were, for example, log-tree2, which is a method that uses biological knowledge about protein trafficking pathway in the cell. It implements a hierarchy of support vector machines in order to predict protein localization at a very high accuracy in 18 classes. I was further able to improve this performance by mind-blowing 15% just by plugging in a simple blast. This method was log-tree3. And then I used this knowledge, this already available information, to solve another biological problem. And that was the prediction of type 3 bacterial affected proteins. These proteins, they are pathogenic, they cause terrible diseases in animals and plants. And this problem was considered before to be a very, very tough one. Because from biology, we know that the whole apparatus that is responsible for pathogenicity is very well conserved. However, type 3 affected proteins are not. However, again, using the knowledge that we already had before from our previous approaches, we were able, just applying the same procedure, we were able to achieve very high results. And this way we solved this very tough problem. So these were just 3 applications of machine learning, but as all of you know, the number of applications is actually endless. And to be honest, you know, being here right now and having this tool in my hands, this knowledge of how to use machine learning, honestly, I consider myself being very, very lucky having all of that. All right, so these all are the buzzwords. Everyone likes to use them, everyone likes to hear them. However, the distinction between them is not always clear. So, the term artificial intelligence was formed in the 1950s, when the first machines were built to work on one specific task as good or maybe better than we humans can. For example, playing chess is an example of a narrow artificial intelligence just specialized for one particular task. These methods, they remained out of the spotlight for quite a while until these methods, they became intelligent by plugging in machine learning approaches. So these methods, they were rule-based, but these methods, they learned from the data and they learned how to make predictions about the world. So they became intelligent, they became very, very effective. However, even having the best machine learning approach, we were still too far away from the goal, the dream of science fiction, and that's the dream of general artificial intelligence. General artificial intelligence, these are those machines that have something like our knowledge, that have our senses. Those are the machines that can think like us. So this is the goal. We are here, we're still far away from it, but everything changes again. And this happens around 2012, when we learn for the first time how to use huge networks on the huge data sets, having huge set of parameters. So these deep networks, they allowed us to outperform any approach that existed out there before. These methods, they brought us a bit closer to this general AI dream. As a matter of fact, when I was preparing this presentation, I stumbled over a paper by Google's DeepMind that is today a week old, that says that, you know, guys, we have a different network now. Now we have networks that learn on several data sets, they learn several problems, and then you can use this network with already available information. And based on the previous experience, this network is going to optimize even better for your problem. So this network is going to be so general that it can actually think, it can actually adapt to the problem that it's trying to learn right now. So now, a week a week ago, we got, again, a step closer to this general AI dream. Even though the general AI devices do not really exist yet, we know many of them already from books and movies. My personal ones are, for example, this Hell guy from 2001 Space Odyssey. That's the Terminator. These are the robots from Star Wars, Wall-E. And my top favorite one, because I know him since I was this big, was the spaceship from a novel written by a Soviet guy. And the book is called Andromeda Nebula. And what's about is that a crew, a number of people, they decide to travel to a different solar system, maybe you know. And of course they make mistakes, and of course they get into trouble, and of course they fail at some point to make meaningful decisions. What happens is that the intelligent spaceship realizes that problem and takes over the part. So from that time point, the spaceship makes intelligent decisions and does absolutely everything to save the crew, and eventually it succeeds. And when I was this big, I was thinking, amazing. But back then, I had no experience with computers or whatever, but I believed that this is going to be possible. I knew that we will develop such machines, and I knew that it's going to take a lot of brilliant minds, genius minds. We will try, we will fail, but at some point, we as a humankind, we will achieve something like that. I thought, wow. Okay, so where did it all begin? The trick usually is that when we want to develop something new, we borrow ideas from nature. When Da Vinci was developing his flying machine, he also was looking at birds. He was looking how they fly, how they move their wings, etc. Just the same happened to AI as well. Already in the beginning of previous century, a French neuroscientist, Louis Lepic, he described for the first time mathematically a model of a cell neuron. He said, okay, if we use a simple electric circuit with a capacitor, parallel capacitor, and the resistor that mimics the behavior of the membrane, then we can model the following. If we have our capacitor and it gets charged, and at some point it's going to reach a threshold potential. If this happens, then actual potential happens. So something happens, and then when it happens, then this capacitor gets discharged and gets back to its resting state. To translate into normal language, if a membrane gets some kind of input, if the input is so strong that it reaches a threshold, then something happens, the membrane reacts, and then it goes back to its regular state. He also looked at the frequency of these membrane responses here, and all of this he modeled with formulas. The formulas, I looked them up. I didn't put them on the slide because I thought there is no space, but I can tell you that they're very, very simple, and the beautiful part of it is that these formulas are still used nowadays. Maybe also one interesting story about this scientist is that his wife, she was also a neuroscientist, and he insisted already back then that on all of his work, his wife is going to be mentioned as an equal co-author. And for me it's amazing, because if you look at the date, women did not have that much voice yet. I thought it's cool. After this research, there was a whole bunch more research done on neurons, and I picked these three that I found especially interesting for myself. So one of them was done in 1952 by Hodgkin and Huxley, when they described even more sophisticated mathematical model of neurons. And the beautiful part of it was that they described perfectly how it functions mathematically without understanding how the membrane looks like, what the biology of the cell looks like. That was a breakthrough. Another important discovery, in my opinion, was done by Hubel and Wiesel, who were researching human brain. They said, well, you know what, guys? Our brain is made of a bunch of cells, but this bunch of cells is not random. Actually, cells, they communicate, and the communication follows certain pathways. In particular, they studied visual responses to light. The third achievement was done by David Marr, who within 3 years wrote 3 solo author publications on mathematical models of 3 parts of our brain. When he wrote these papers, he was between 24 and 26 years old. And he is also the guy who said, you know what, people, in order to succeed in the brain research, you need just 3 components. Component number 1, you have to understand what is your problem. Component number 2, you have to understand what is the algorithm to use. Component number 3, you have to implement the algorithm correctly, and you have to understand what is the outcome of your algorithm, how to interpret it. He said that for any problem, there can be many solutions, but to succeed, you have just pick one solution, go deep into it, and then you will succeed. And I think that's a very, very good advice that all of us can use. I want to introduce another face and another name, and his name is Warren McCulloch. The previous guys, they were working on mathematical models. He, for the first time, he implemented a neuron. If we look at the years when he was working, it was 1940s, middle of the war, when they were working on that. He was also a poet, and he said, back then they realized what they're doing, that's like building castles in the air. The castles in the air, sometimes they fall down because they break. What we do, we build them again, we fix them, and then we bring them up. And I think that this poetic allegory is very interesting when we talk about informatics. I think that we never looked at it that way. So what's so special about him? He was a professor at the University of Chicago. And at some point he ran into when he was over 40 already, he ran into a student, 18 years old student, who was homeless. And they started talking. They realized that they have many interests in common, and he invited him to live in his house. Well, they had a lot of time to talk and to work together, and they were thinking, well, how can it be that our brain that is so complex is made of such simple units, our cells? How can we model it? And they came up with that. And that's a neuron, that's the model of a neuron. A neuron gets a number of inputs, it can be any number, and these inputs are binary. And the output of a neuron is binary as well. In order to model the output of the neuron, you simply sum up the weights. If the weights exceed the threshold, then the neuron has either one response or the other. It was beautiful because using that you could model mathematical functions like and XOR, and bam, that was the birth of a neural network. That paper, when I was preparing this presentation, when I was looking for the paper, I saw that people, they celebrate this paper, the birthday of this paper every year. They organize parties, they organize meetups, because it was just so big and so huge, and it created a lot of excitement in the community. Well, back then, people could they could work only with a bunch, like a few dozens of neurons, just because computational capacity was not available yet. Here we're looking at the Moore's law chart. However, this was changing with time, and if we look now where we are right now, we see that our computational capacity allows us to model a mouse brain. If we look a bit in the future, like 2030, wow, we see that we can already model a human brain. And these are the expectations with neural networks. Okay, I did my research, and I found that we're actually behind the schedule because even though we know so much about the brain already, even though we have 3D images of the brain already, it's still going to take another 300 years to connect all the neurons with each other, because this puzzle is so complex that the bunch of researchers who work on the human brain, they just don't have this capacity to do that. So what did they do? They came up with a brilliant idea of involve everyone into that project. So they organized this puzzle game where everyone can join, and using the knowledge, experience, as well as the help of artificial intelligence algorithm, people can connect the neurons in the brain. I saw that last Saturday there were 200,000 people playing the game, and Probably this number is still not enough, and probably we're still not going to have a model of the brain by 2030, but I am convinced that this is going to happen during our lifetime, still pretty soon, and I think this is amazing. I think that maybe that should be a little bit of focus of all our research, yes.
So you're convinced we will not have a nuclear war that will set us back to, say, the Middle Ages?
I believe in the good of the humanity. I believe that there is no way of not having general AI machines anymore. I believe that the humanity is going to create only good AI machines. They're not going to use them against us.
Will we have backups?
So you're a religious person, okay?
Well, you know that there are this joke that what if you created a AI machine that is going to learn how to produce, I don't know, be it clama. What is the word in English? Clamps. Yes, exactly. So what is going to happen if that machine will learn it so much that it's going to use the whole world just for producing them? Well, the assumption is that these machines are going to be so smart that they will actually realize that the humanity doesn't need so many of them. That's a little anecdote. All right. So we are far away from this, sort of. But what we already have, that, so this is an American project. We also have a European project called Blue Brain. And Blue Brain published a paper in 2015 saying that, you know what, we have a whole small piece of a mouse brain already in our computers. And this simulation includes 31,000 virtual brain cells that are connected by 37 million synapses. The goal is to use all information about those neural cells, like 3D shape, electrical properties, ion channels, and other proteins they interact with in order to produce such model. And the exciting part of it is that when we stimulate this model, by the way, it's all available online, everyone can look at it, everyone can play with it. If we stimulate this model, then the model reacts just in the same way as the real rat brain does. That's crazy. I think that's a big achievement. You look so skeptical.
No,
that's what they say.
I'm trying to, they try to give it a body and, for example, put it into a labyrinth.
Into where?
A labyrinth. Rats are notorious for navigation labyrinth mazes.
Okay. I will get back to that. The European Blue Brain Project says, okay, right now we have a part of a rat brain. Soon, in 6 years from now, we're going to have a whole human brain.
If they get another billion.
That's not what they say about the billion.
This is the first $1 billion or first €1 billion project.
Okay. It was adjusted for a guy. Now you moved it. I don't know if he still sees me.
I'm sorry.
Guy, can you see? You're muted. Okay, everything's fine. Yeah, but given they would have this $1 billion or euros, 6 more years, and we will have the first results. I think that's crazy. Okay. Nowadays, we know about the brain already so much that we can connect external devices to it to improve the missing capabilities. And this one, I don't know how to pronounce it correctly.
Cochlear.
Thank you. Is one of examples of them. So what happens here is that a patient gets a surgery and it gets this device connected to its hearing nerve. Outside on the head there will be a microphone that will listen to the sounds. And then the sounds they will be transmitted to the nerve directly. And what happens is that if you implant this device in a baby, then the chances are that this baby is going to develop language skills just the same at the same level as healthy hearing other individuals. So with these implants, we actually have already solved the being deaf problem. And in the States only, there are, I read, 300,000 devices that are being implanted in adults and children.
Where's the battery? Where's the battery?
There is a big device here, like attached to this part of the hand. And if we think about that area more, then you will realize, I realize, that we live in the future already for a long time. Already in the 1960s, the director of NIH, he coined a term called neural prosthesis. That is a device that links brain to this device with the goal of recovery of motor and sensory function to patients with neurological conditions. Just imagine, in 1974, there were already studies that helped to restore vision in patients. In 75, there were studies that restored leg paralysis after spinal cord injury in baboons. In 1999, this is back to you, Dmitry, there were studies that showed that mice, rats, they can control simple robots just with their thoughts. I think that's crazy. I think that's an area that is endless and where we contribute still so much. She's eating something.
But just a few years later, the first one who actually moved something on the screen was a tomb through an implant. Jerry.
And what I want to say here is that the idea of connecting our brain to something is already available in nature. Coming back to examples from nature. So this is an example of two girls who were born in Canada in 2006. And these girls, they're connected by their skull. So their brains, each of them has a brain, but these brains, they're connected through a bridge. And even though these girls, they have their own personalities, they still, through this bridge, can see through each other's eyes. They still can share emotions. And they still can share thoughts.
Are these emotions and thoughts shared by default, or can they do it arbitrarily?
This I don't know.
Okay.
They're also very young. So maybe there will be more studies done on them later. But looking at this example, I start wondering if maybe one day it will be actually possible to link our brain to a computer directly. Maybe, this is my assumption, maybe it will be possible to swallow a pill, and then there will be a device grown in our brain that will connect us to a computer. And
the Tom had the first device that connected the brain to the mouse.
The brain to the mouse?
Yes.
To a living mouse?
You can move, so they made somebody move something on the screen.
Wow. That was when?
Just a few years ago. I was still in New York.
Wow. I was not aware of that. So, and how did it work?
I do not know who. So you had some electrode implanted, or?
Okay. But I think, so apparently this is already possible. And I think that if we will do this on a large scale and will connect us to the real computers, I think that something completely crazy can happen. I mean, once we have already changed ourselves by introducing new technology. And that technology was when we learned how to make fire and to cook our food. When we did that, we did not realize that the nature is going to favor now not those humans who have stronger teeth, but those humans who have weaker teeth, because we don't need weaker teeth anymore to chew on cooked food. And that's when our skulls became larger. And that went completely against all rules of nature, because there are no other animal that has such a big head size in comparison to the body size. And I mean, if already now every one of us has a smartphone, and this is normal to use it, I don't know, every 5 minutes. And maybe having this device in our heads that will connect us to a computer will also be normal. And maybe if that will be the case, this is just a play of thoughts, but that's what I think. And maybe if this will be the case, maybe then we will evolve not in parallel with computers, but together with computers, and maybe we will become some kind of semi-synthetic new humankind. Yes?
I think it's going to happen because it's a great way to solve the Earth overpopulation problem. How do you take humans and put them in a storage space? You put them into virtual reality and you put them into a warehouse. That's it.
So I have a comment. I met once a training pilot who was training on a helmet that essentially can read brainwaves. And because the pilot needs to make a decision really, really quick, they developed the helmet in a way that some of the functions that are usually being handled through the hand or the leg, something like that, now it's being delivered through brainwaves. And that's how they shorten the reaction time.
So that was a project or that really works? There was a future project or that works?
The one that crashed.
No, that's actually...
That's the one that was crashed.
was a guy who was sent from here from Israel to one of the top secret U.S. facilities to essentially train the people there how to use the helmet.
Wow.
That's like a real story. I'm not making it up. It's not like something else.
Which year is that?
2012, I think. Yeah.
Crazy.
2012 or 2013.
But you see where the shift is going to, and you see that like right now we are just at the beginning of a new era. And from my experience, when I was looking for a job, I was very pleasantly surprised seeing that people like us, they're very much needed. What people are looking for is this machine learning skill. Everyone at every interview, at every company asks, so explain me how it works. And what you need to answer is that, well, I have to get my data. I have to clean my data. I have to organize it. I have to find a machine learning model that fits the data. I have to optimize it. I have to get the result, and I have to be able to analyze the result. Really, it is always the same recipe for any problem that can be solved with machine learning. And yeah, it applies to absolutely any industry, not only to healthcare. And I think, guys, that being here in this group under Berkeley supervision, we have absolutely everything to learn the skill to be perfect. So I want to encourage, especially students, younger students, to use this time to learn the skill, and maybe also to pick another skill, be it, I don't know, present at a large conference, or manage people, or write a blog post on Google. Just pick a skill, get out of your comfort zone, and work on it, and have it done. Use the time. You have this time now in order to prepare for your dream job. No, I'm not done yet. And my other advice would be to have fun in what you do. Very often it's boring to work on a specific task, or the task is too hard. But I encourage you to look at the results of this task, because looking a bit further about what the goal is, you will realize that this is all worth the effort. And if you will work hard, if you will deliver quality work, and you will be honest with what you do, you will deliver 100%, then believe me, the community around you, if they will see this honesty, they will give you so much more back, way more than 200%. And this brings me to my final slide, where I want to say a big thank you to Burkhard and to the whole team. It may sound pathetic, but this is me personal, this is real me. I will tell you that being here in this lab, these were the happiest years of my adult life. I worked hard, at least I tried, and I had an immense number of successes, and I celebrated all of them. Most important for me were the people. I learned so much from working with those people whom I worked with. I made friendships that I hope will last my lifelong. And I want to thank you guys for this amazing time and for giving me this amazing start into my professional, adventurous life. Thank you. Thank you, and please have the sweets.